All you, sir.
All right, welcome. My name is Jaime Machuca. I am going to present about the duckling droids that we've been building here. So a little bit about myself. I'm a robotics engineer in real life, and I came here last year for the first time, and I was really amazed by all of this community. And it was only in March of last year that I was fortunate enough to be at GTC in California, and I was able to see these droids live for the first time, and they just amazed me. I mean, from the moment that I saw them, I decided I wanted to build one for my own. And basically, the only way of doing it was to actually build it myself and make everything. So I started looking around, and I found Mr. Battley's Patreon, and I found some of the files there from Alec, which were awesome. And then the other thing that I found was that Disney had actually published a paper, which is the design and control of a bipedal robotic character, where they basically spelled out all of the things that they did to build these robots. Basically, they say what kind of actuators they have, how they control them, how they did all the training, and all that. All that's spelled out to that, and there's links to other papers that show you how to do all of the other training and all the other parts that are there. So the first thing that I started doing was trying to figure out how to reverse engineer this from references and screenshots, because the files that were existing didn't match exactly what the Disney motors had. So I had to modify some of the leg parts, some of the other parts, to make it more exactly the same as Disney. And the reason that I wanted to make it exactly like Disney was to basically reduce the complexity, because I already knew that what they did was working, and I didn't want to reinvent the wheel or try to figure out or try to fall into pits that may or may not work. So I decided to go exactly with what they were doing. Then sourcing the components was another big part, and finally the 3D printing. So what's inside of this duck? Basically, we have Unitree actuators, which are the motors that we see here, and there's two types of these motors. One is the Go M8010-6, which has 5 of those, and then it's got 6 A1s. And the reason is one of them has a higher torque than the other one, so it gives it a little bit more power in certain parts, like the knees and the hips. And then it's got also some dynamixels on the neck, which are the ones that are moving the head, and then it's also dynamixels on the ears. That's the part of the actuators, and the power that it's using the Go battery from the Unitree as well. Inside of it, the brains of it is Jetson Orin Nano, and there's actually 2 of them. There's one in the body and there's one in the head, which you could actually, it's probably a little too much for what it's actually needing. You could probably do this with a much more smaller compute module. Like we have the Mini, which I'll talk about in a little bit more. These guys are basically doing the walking and all the inference using a Raspberry Pi Zero, which is a really, really small compute module. No problem. Then there's a couple of heads. So last year I came here and Mimir was here. He couldn't make it this year, but basically he has designed two boards. One is the quack head, which goes in the head, and it just helps reduce the wiring that goes on the robot. And then there's another one which is called the puddle duck, which goes in the body. And this one is a little bit more important, because the way of the motors are connected is they're using an RS-485 bus, and you can only connect a certain number of motors per bus. So we need actually 6 RS-485 buses to control the whole duck, and the Nano by itself doesn't have that kind of input-output. So Mimir designed this board, and it's using a Teensy to connect to all of these things. And I'll go a little bit more into the hardware architecture a little bit further. Other parts that are there are cameras. I have 4 cameras, 2 in the body and 2 in the body and 2 in the head. And then I have a depth camera in the middle, which is the Oak D camera from Luxonis. And this is kind of what Disney was doing. They just recently added those 4 cameras. They presented them at the last GTC this March, and the droid that they presented there had these cameras already. I'm using a little bit wider field of view cameras because it's just what I was able to find. Then we have 2 displays for the ears, which are just round LCD displays. I have 2 USB hubs, one in the body and one in the head, to connect the cameras and all that to the Orin Nano. the Dynamixel bridge, with bridges between the XH540, which are in the neck, to the ones that are in the ears, because they're different control buses. One is RS485 and the other one's TTL. And then I'm using also a CarTech E stop, which the Disney were using, which in the end proved to be a little bit unreliable. So I am actually bypassing that for now. But it's still part of the aesthetic of the robot, so I still have that there. And that uses an optocoupler to connect to the input-output, and then a battery board and some power distribution boards that are there that were also designed by Mimir. The next part of it was, of course, 3D printing the parts. And I have 2 boxes of parts back there for anyone that wants to take some parts that are not, they were parts that have little defects, or that I didn't like, or that I changed something on. So there's a bunch of parts over there if anyone wants some to get started. And then the other thing that I didn't take into account was the number of screws. This thing has approximately 280 screws all over the body, and that was just a massive thing that I just completely underestimated. These are some of the pictures from the robot without the cover. So you can see here that it has the puddle duck around the dev kit board from NVIDIA, and then this is the optocoupler that connects to the CarTech E-stop that's on the back. Then we have the 2 PDV boards that are on top that connect to the motors, and then all of the buses connect to the puddle duck, and then the puddle duck connects to the ORIN via USB cable. And then this is just an exploded view of the leg, where you can see the 3 different motors that are there. Going a little bit more into the hardware and software architecture. So I'm a software engineer. I'm not really mechanical or anything like that. So the mechanical part of it was completely new for me. But this is more of what I'm more accustomed to working with. So this is basically the architecture that is working. We have the 2 Jetsons controlling everything. To the Jetson, we have some speakers connected. This is the body Jetson in here. We have some speakers connected to the 2 cameras on the body, the OGD, which is the depth camera. Then we have a Cube Mini, which is basically an IMU that is what's reading the position of the robot. And then the Jetson connects to the Teensy via USB, and then the Teensy controls the rest of the stuff, like the Unitree motors, Dynamixels. They're all connected into these 5 different RS485 buses. So you can only connect 3 motors per bus. So we have 3 A1s from one of the legs, and then we have the Go motors on another one of the buses. And then on the other RS485, I have the Dynamixels, and then we have the Quack head board on the top, which is basically acting as if it was a Dynamixel, and it's communicating with the rest of the board. So Mimir designed that software so that it would communicate that way with the rest of the system. And then that Quack head board has an ESP32 in it, and that's controlling the LCDs on the eyes, and it's also controlling the sounds that come out from the speakers on the head. Then the battery also has an RS485 bus that connects to the Teensy, and then we can read the voltage, the current that it's currently pulling, and then also all the voltages from the individual cells on the battery. And then we have the E-stop going there, and then we have the little NeoPixel strip on the front that is also connected to that Teensy. So where are we currently? So one of the first things that we need to do is make the motors give feedback to the system, right? So, and then also the observations from the IMU, which is what is needed for what we call the policy to control the robot. So one of the first things that we have to do was start the communication with the motors, and then give that feedback over to the system in the robot. What I'm using for this is basically ROS2. So all of this robot is completely controlled by ROS2, and it's interfacing to all of the different components through there. And that makes it easy to add and remove components, and kind of forces you to make it a modular system. So there's a node that controls the motor. There's another node that reads the feedback from the motor. There's another node that runs the policy. There's another node that sends the data back to the user, to the controller. There's another node that reads the joysticks, and it's all basically modular. So if I wanted to use a different controller than that, it's just a matter of changing one module, and it will be able to control the whole system. Then we have, or what is being, or what I want to use the cameras for in the future is for the navigation side of that. So the cameras will be able to map the environment around it, and then it could plan a path around different obstacles or follow a person or something like that while still trying to navigate around those obstacles. And that's the future work that's coming. This is just basically a video of early video of it working and moving the motors, and then I have the feedback on, this is called Foxglobe. It's a visualization software for ROS, and you can basically see that. And that's what kind of what's currently running on, well, actually it's not what's currently running there, but I'll show it to you in a minute. This is the same thing. So here you can see that we have access to this is the battery voltage, and it goes from 0 to 24 volts. So it kind of gives us an idea of where it is. Then we can look at all the data, the raw data from the sensor. So this is the data from the IMU, and I can look at all the different data that coming from there live, and as well as plot that information on the board. All right. So the next thing that needs to be done is the way that this is going to be made to walk is by training it, and it has to basically learn how to walk. And one of the issues with that is that you could run that software on the robot and try to make it learn on the robot, but that's going to break the robot a lot of times, right? So the way that you do that is by using simulation. And the caveat with that is that you need to have the robot be able to respond the same way in the simulation as it will in the real world. So one of the first things that you need to do is characterize the motors and how they respond to stimulus and to control commands. And that is something that was done by Mimir. You basically put a weight on the motor and try to give it certain inputs, and then check those inputs and graph them. And then you can basically create an equation that mimics the motor very closely. And if this does not mimic the robot exactly as it behaves in the real world, if you train it, it might walk okay in the simulation, but when you try to put it on the robot, it's going to fail and it's just going to fall. So that's one of the very important things that needs to be done. The other thing that needed to be done was the 3D model, but the 3D model has to be very accurate regarding the weight and the balance and the center of gravity, and all that has to be modeled exactly as it is on the robot, so that the simulation responds the same way. And in that instance, there's been help from several people in there, and Sai is one of the ones that has made some software that translates from the Fusion files into an URDF file or a USD file. Basically, that is what is used by the simulation software to mimic the robot. And then once you have that, then you can start doing the training. And this is a video from Mimir, from his early parts of it. And as you can see here, the robot is actually walking, but it's not walking like the Disney robots are walking. So this is basically just training it and telling it, well, you have to walk. And the way that you tell it that is you give it a reward. And whenever you want it to when it starts doing what you want, you reward it more. And then it starts learning what you want to reward more and more and more. And then it starts walking. But in this case, it doesn't have a target on how you want it to walk. So it just learns to walk however it learns to walk. So the next step of that is to do what we call imitation learning. So for that, you actually have to feed it a target. And for that, we do animations. And then once you have those animations done, you basically reward the learning when it gets closer to the animation. And that is what is done on this imitation learning. And then once you have that, then you have to put it onto the real robot. But we found, or Mimir found very easy, that the head was a little bit easy to break. So one of the first things that he did is he had to retrain the model without the head so that he could test without the head in the real world. And basically, this is a video of the policy running after it's been trained. And you can see that the red lines is basically simulating that you're pulling or pushing the robot, and you can see how the policy responds and balances the robot. And then the next step is actually running it on the robot itself. And this is him trying to run the policy on the robot. And and just trying to move the legs over, and then you can see on his computer how it's supposed to be moving, and then this is basically the feedback from all of the different sensors on how it's moving around. And that's kind of where we are currently on the development of this. This is one of the first tests of it walking, and it did do a couple of steps, but then it fell, right? So there's a lot of that going on currently. And there's broken parts from the motor sides. There's broken parts on the legs. So it's been back and forth. These are basically probably from a couple of weeks ago. So we're still working on the walking. The next step is trying to get it more stable, and hopefully it will be walking soon. The other thing I wanted to touch on is the OpenDuck Mini, basically. So this other software was designed by Antoine Piron in France, and it's a completely open source robot as well. And this one is actually a little bit further along than the full size. And in this case, I have the same software that's running on the full size. I have it running on this mini dock, and it's basically the same thing that I run there. I can run on the other one, and it's just a difference of the policy. So the policy trained for this small dock it's the only difference than what I'll be running on the full size. So I'm using the mini one to test all of the software before I actually put it on the big one. And this one actually, it's supposed to be walking. So this one is actually walking a little bit more, and I did some tweaks so it actually walk that way right now, but I can do a small demo there. And we have a Discord where we're communicating and where we're sharing all of this, and that's basically the link to the Discord if you want to join that. There's a lot of information there for the mini dock especially, but once we get a little bit further along on the full size, we'll start posting, also opening channels for the full size on that Discord, so that we can share more and more of this information here. So with that, I can open up for questions. Yeah.
We train one of these. Can we transfer that to others so we don't have to retrain each and every one of these?
Yeah, so that's the yeah, maybe that's something that is not really understood on this, but once we do the training for the robot, that training is generalized a little bit. So you basically tell it to model differences in weight, differences in the response on the motors and all that. So it should be able to handle different builds. So if I train something, I can give that to you and you can run it on your robot. And that's what's been happening with the mini dock. So that policy that they trained for that is actually pretty robust. The servos that are on there are 7.4 volts. And there's people running servos that are 12 volts, which basically behave completely different from the 7.4 volts. And the policy is still is able to walk with it. So it seems to be very, very robust on that sense. Any more questions? No? All right. One more question.
How forgiving is the learning and training with the different servos?
What do you mean? Like how?
I mean, like, so you're using servo X and someone else isn't able to get that particular motor. I know you said that, the ones that are running on 12 volt or 7 volt, but I mean, is the policies pretty forgiving on that, or is it you need to stay within a certain parameter? You
need to stay within a certain parameters, but at least on the OpenDuck Mini, the policy has been able to walk with the 12 volt servos. It doesn't walk as stably as it does with the 7.4 for sure. But retraining the policy for the 12 volt is just a matter of changing. It's just a matter of running the training software basically. But the difficult part is you need to characterize the 12 volt motors before you run that policy. And that's something that it was just done yesterday, actually, by Antoine. He characterized the 12 volt motors and retrained the policy, and people reported that it did make a big difference on the standing policy, basically. But on the full size, I'm just probably gonna say it's gonna be a little bit less forgiving, just because it's bigger and the differences are bigger. So yeah. No, there is. So the IMU, if I go back here, the Cube Mini has 3 gyroscopes, 3 accelerometers. It's a triple redundant system, and it basically it's an AHRS system. It's not just an IMU or a gyro. So that gives me the position of the robot in real time. So basically, this is this is the software that I use to visualize, and as you can see, I have the model of that's the URDF of the robot, and it's getting the feedback from the motors, and it's moving the real time the same way that the robot is. And then the top one is the X and Y positions of the robot. So if I move the robot, you can see that it moves, and that's the information basically from the gyro and the IMU coming, and that's what I'll feed into the policy, and then the policy will act upon those inputs and output the positions of the motors. And it's gonna be running, or we're planning to running it at 50 hertz, so 50 times a second. Yeah, that's it's just part of the policy. That's what it will do. We're still investigating if there's the same policy that's going to be used for walking is the same one that is going to be used for standing, because I think at least the Disney system is switching policies between walking and fast walking and standing, and then they also have different policies for when they do the little animations where they like shake and dance and all that. Those are different policies that run, and they switch on the fly between one and the other. So that's one of the things that's still, well, we got to get it walking first and standing. So thank you.
So I saw Mimir's presentation last year, and it was fascinating. It looks like a lot of progress has been made in the last year in terms of getting them up and moving and walking. Out of curiosity, do you have a sense of how much, when you think he's going to be really walking without falling over, or really getting more to the Disney side of it?
I don't know. I thought I was gonna have it walking by now, basically. I think we're really close, but it's just, this is not our full-time job. So Mimir has other things to do. I have other things to do. So it's just taking longer than we expected. But I don't think there's any blockers. I think it's just a matter of walking through the steps that we have to walk through to get it walking. And right now the issue has been the policies that you saw trained on the presentation. They were trained with another, when we didn't have the motors characterized exactly. So these policies, they walk very well in the simulation, but when you put them on the robot, they don't react the same way. So that's why Mimir decided to start characterizing the motors again, so that we can retrain the policies with those new characterizations. And then the other thing that we need to do is we need to modify the URDF, or the model for the robot, to mimic the weights of the robot a little bit more, because we initially had the whole body as one rigid body, and the battery is on the back of the body, and it changes the center of gravity significantly. And the way that we were modeling it, when we exported it from Fusion, it was putting the center of gravity in the wrong place. So that's one of the other things that we need to continue doing, and we need size help for that, if she's here. I know she's here. I don't know where she is. But yeah, so that's another thing that's stopping us. But I think it's just a matter of moving forward and walking through the process.
I can talk about it.
Yeah.
Hello, online people. So, do you feel that the hardware and the mechanical design is pretty much locked at this point, and it's really more of a software thing, or is it still getting just fundamental tweaks to the hardware and the boards and motors, those sorts of things?
Yeah, that's a good question. The hardware side of things, I think it's pretty much like the type of actuators and all that that's there. It's probably locked. The mechanical design of it, I think this one is very, very close. But we've been having problems with stress fractures on the parts. And for example, the leg parts are deformed. So the A1 motors have a ring around them. Let me show them. Okay. Here we go. So the A1 motors have this ring around them that basically keeps them aligned, and that part is not on the robot. That is basically part of the leg that is holding that alignment on the motor, and we found that it's basically falling out of alignment because the part starts deforming. So there might be some changes to those parts to maybe make them more robust, or more likely we're going to have to make them out of aluminum. So it's the leg parts, and then the hip, the part that connects the leg to the hip has been breaking very frequently as well. So I think we're going to have to change that part to aluminum as well, probably. Yeah, so changing that will affect the model. No, because once the policy is trained, you can basically use that as a base and then retrain it with the new parameters, and it shouldn't take as long as it took the first time, for example. So you should be able to adapt it once you have those changes. Yeah. All right. Well, if I'm going to be here all weekend, so if you have questions, I'll be back there. So thank you.
Can y'all hear me? Testing, testing, testing. 1, 2, 3. Can y'all hear me? Okay.
Hey, listen up.
So we have a special guest. So I am going to do some introductions after this. It's hard to top this amazing presentation, the BDX droids, because they're adorable. Did you see that they were in my presentation today? Yes. So, but anyway, we have a very, very special guest. Some of y'all probably already know that this person is coming. His flight was delayed, but we have a very, very special guest. But before that guest, we have some more surprise guests. So let me just check and make sure they're ready. Okay, here we go. Your very own. Wait, Michael, that's not the right one, right?
No, I had to bring some more English people with me, so we've got another one. We have more. We've dragged another English person here. And we've also brought our partner in crime.
We've got one more as well. Come on in. Come on in. Okay. That's not necessarily a bad thing. Hi, guys. Hi, camera. So we actually arrived yesterday, and we've seen most of you wandering around here that have been here for the last 24 hours, trying to sneak around so that none of you saw us. Today, we were in the zoo just to get away from you guys, because otherwise we'd have been sat in a very warm hotel room, but which I have done for the last 3 hours with him, which was an experience, I can tell you. But I'm going to pass you over to him now.
Oh, no. Yeah, so in the lobby today, coming out of the elevator, just boom, here's some builders right there at the main desk. And it's like, whoops, and around, and nobody saw us. Then we went to Subway, and they said, oh, a bunch of builders just left. So we've been dodging you guys for 2 days almost. So.
Let's talk about what just happened like 2 or 3 minutes ago. That they walked right past Matt Hobbs, and he did not recognize them.
So I've been talking to Matt via message all day saying, have fun at the con. Surprise.
Well, I mean, so anybody that's in the North American Droid Builders chat will know that I've been messaging all day, wishing everybody to have a fantastic time. Spanners, I set you a goal 6 months ago to get your legs ready to be here. I knew I was coming 6 months ago, but I wanted to make sure you were here, so well done on that. My partner, who's over in the UK still, she's been sending me photos of my new workshop build, which I've been posting on my Facebook and in Droid Builders chat to make it look like I'm still over there. There's been lots of stuff going on. So on Saturday, you may have noticed that there's a talk by the 3.5 Amigos. That's us. Sorry. But there is a half. Unfortunately, he couldn't be here, but Lee Towersy was meant to come with us. He can't. Sorry, Lee, you might be watching. Yeah, for sure. But he is going to tune in on Zoom on Saturday, so he will be here live on camera to answer questions as well. So Lee will be joining us remotely. And hopefully whenever we do this again, which I'm sure will happen at some point in the not too distant future, he'll come next time. But yeah, really excited to meet some of you that I haven't met. Really excited to meet the people that I have talked to over the last couple of years and never met. And really excited to see the people that I've known for many years already. I'm Doug, by the way.
This is Doug. Yes, that's John at the back.
That's John, right? Okay.
Yes. Yeah, I believe this is the last one before celebration, isn't it? Because we're taking it. Is it? We don't know. We need to know because next year we might bring more people. Cool. Anyway, I think it's time for a beer.
Yep. After Hours has officially begun.